G'day viewers, just a bit about neutrons, just to give us a bit of a background. It's probably like chapter 3 in the book, but we'll just get it out of the way. You're looking there, it says mean life of 881.5 seconds plus or minus 1.5 seconds. Yeah, that's the mean half-life. You know, at the upper end of the bell curve, you could have, you could have stable neutrons living quite easily twice that, and the odd one even longer. We're just looking at a neutron contains a proton and electron, and there's a little bit left over, and that's usually, as you see I've written there, an electron neutrino, or an electron antineutrino, and a gamma ray photon. In those combinations you can have, there's some forbidden combinations there, but there's some absolutely proven. Look, I don't have to do the experiments, so I've got the results of the experiments. You can Google it yourself and read up. But neutrons are very important in the whole symmetry, asymmetry argument. You know, if you're going to argue a universal field theory, which I think Gary from Draft Science, I think he's probably pretty close there with what he's come up with. After I've done some analysis, I listen to everybody. I listen to the Electric Universe people and Eric Verlint with his amazing theory, but his isn't even complete yet. It's pretty good if you want to read it. Yeah, the old neutron, it's got a little bit more than just a proton electron, and that tiny little bit of difference changes the whole outlook of the picture that we form of the universe at a quantum mechanical level. And what I think Draft Science is postulating there could have major implications, and we'll see some of the results. I've done some working out, and I've done a bit of reading, and you know, it's mainly mental thought. You've got to really put some thought in and say, well, does this obey the basic laws of physics or does it not? And I think these primordial force bits that Gary talks about, I think they existed before even quarks existed, before the quark soup. You know, so many billionths of a second after the what they call the Big Bang. And that's a whole nother story. You know, science, they can't understand the Big Bang. Well, I've got my own version of the Big Bang that fits right in with all this, and I would like to say that it's my opinion, after a lot of thought over many years, that the actual Big Bang is one case where a singularity did occur, and it wasn't just a singularity. I think it was a singularity that developed into a major rip. But that's another theory for another video a long time in the future. And a lot of you won't like the answers that I've come up with. So I'm prepared to argue with certain people. I'm not going to argue with everybody. I don't have the time. I'm just going to put it out there, and I'll show you what I've come up with and why it works. And it works so well once you start. It's like when you do solid state physics, you got to take into consideration hole flow as well as electron flow. So you've got these moving holes moving in one direction, and electron charge carriers moving in the other, and that's pretty amazing. So let's just have a microscopic view at Draft Science's postulations and how he thinks things work, and I'll give you my interpretation. Whether I'm right or wrong, I don't care. This is just what I've worked out. And what he's saying is, let's just deal with colours. I would like to have red and blue. That's the traditional magnet colours, but and I apologise for the phone held video, because I don't have a HD video camera. I spend my money on other things, like a lot of money on experiments, as you'll see. Some pretty crazy ones coming up. But we'll look at the magnet, and Gary says there's two types of force bits. Yeah, it's a great concept when you take it. When you step back and look at the big picture. So we've got the red. Now they come out of this red end, and they try to come out straight, but what happens is, because they're all the same, well, let's use electric charge. They're not. It's a magnetic field, but you've got to have the electric charge analogy. What they're doing is they're pushing away from each other, and the first thing they're doing is they're looking for their mate, for the opposite charge, and the same thing is happening here at the same time. Now this is a static field, it's not moving, but any interference will travel down these lines in both directions, like the black travels to here, and the red travels all the way to here. And I said this was the magnetic neutral zone. Okay, Gary didn't like that term, so I'll use a better term. It's the magnetic equalization plane. And there's things going on here that a lot of people just don't seem to get. And why it's bowing out at the side is it's because this side here is trying to push away from this. Like charges repel, and unlike charges attract, like down this line. So you've got this force pushing outwards, pushing the field out. And I know this, I'm only drawing in lines of force as illustrative, so we can get a two-dimensional picture of a three-dimensional field. And what I've written down here is, here's chaos. So you've got all these little charges that are running around doing all sorts of stuff. And I believe all the charges in the universe, well, I believe most of them at any one time are paired. They're paired in a two-charge coupling. So here we've got an organised system, here we've got chaos. And later on I'll be doing some experiments where I'm going to be using a 1 kilogram standard. And there's a reason for that. It makes the equations so much simpler. And you know, you guys can talk about, oh, it's going to work like this and going to work like that. But what about when I start punching numbers in and I start giving you field equations that actually start working out? So I said my little bit on the neutron. So that's what I meant by there's more to a neutron than just a proton and electron. And the interesting thing is the time of stability. And they only give you a mean time, and there are some errors, but it's close enough. You know, the answers they've got there are close enough. So we'll look here, and we'll look at what Gary's force bits turn into. This is very interesting, and it also predicts quarks with more than 3 couplings. So you can have particles with 3 quarks, 5 quarks, 7 quarks. Yeah, it's pretty mind-blowing. I think 7's pretty unstable and highly unlikely. So what do we do? Right, here we go, and this is what you get if you got 2 of Gary's force bits. Straight away, one, we'll call this one the negative. It's arbitrary, and like Gary says, I've probably picked the wrong, but it doesn't matter. One's positive, one's negative. That's positive, that's negative. And straight away they're drawn to each other if there's nothing else, in the local area. So what happens here, if we bring a third one in, right, we bring a third one in here, that'll come into there, that'll come into there, and they'll join there. Now, you can get this double coupling here, or what do we get here? We've got 3 of Gary's force bits, and there you go, there's a quark. And here's the opposite, another quark with a different charge. This one we've called plus 2/3, this one we've called minus 2/3. Now, this is only a very basic, I've only had a couple of days to think about it and put it into action and see what I got about it. That's what I reckon. I think that's a very interesting, a very interesting view. I've been doing this for, I do sort of weird stuff, it doesn't matter. And this is what happens with Gary's particles if they're in a spin. They don't get to join, and they do all this spiraling down, or you can get 2 chasing each other and get this crazy sort of coupling here. But there are other aspects we need to add in. There's a lot more aspects. This is what I call the gravitational, electrical, magnetic, mass theory. What was that S for? I think it was spin. Yeah, we've got to add. You've got to have spin in the equation. Now, there's already been over 1 million experiments carried out, so there's enough data from most of these experiments for me to be able to analyse them, so I don't have to go out and buy a collider or anything like that. That LHC, you could just about predict every particle that they can manufacture there. They're not stable, they're not worth it, they're no interest to me. They're just trying to get a deeper understanding by spending billions of dollars. And if I was running CERN, I'd be saying, look, there's a big particle coming around the corner, just give me another billion, we'll be right. There's an unfortunate aspect that you've got to follow the shepherds, you've got to stay with the flock, and I don't buy it. I'll do my own thinking, thanks. I'll do it independent. And